Okay, so 12 o'clock, we'll look at getting started. So Mon announced yesterday that it was dropping the mask mandate. Given that masking is still heavily encouraged, I don't know why they bother, but anyway, I'm going to carry on wearing my mask. I will always have masks available here. It might be a good idea, if you reflect back on the last 2 years, how many of you had colds and flus while you were wearing a mask. That might influence your choice going forward in cold and flu season. And we might all be aware that none of us can know if we're contagious at any given time, and we can never know if any of our neighbors are medically vulnerable or not. So the choice is up to you. I will not force anybody to wear a mask, ask you to leave if you don't have one, apply any pressure. But I'm going to wear mine, and I'm going to carry on bringing masks. So if anybody wants one, you're always welcome to it. Next week is a funny week. So Monday is Thanksgiving, so we're off Monday. Tuesday is midterm break. You're off and I'm not, sad for me. Wednesday is the really funny day. Wednesday goes according to Monday's schedule. So whatever classes you normally go on Monday, you need to go to, I guess you don't have to go, but anyway, they're on your schedule for Wednesday. So Wednesday is a Monday. The impact for our course is that those people who are in Monday's labs have a lab period on Wednesday of next week. I can't remember the date, the 12th, 11th? Who remembers? 12th? So Wednesday the 12th, there is a lab period. That lab period in particular is going to be problem session 2. So next week is a problem session. So Monday's group has it on Wednesday, Thursday's group has it on Thursday. So plan to go to the lab next week. The problem sessions are graded, so it's part of your grade. I don't know that I explained how the grading structure worked. I might have forgotten. So the problem set, I give you a grade out of 20. You get a base 10 marks for showing up and working during the first hour. So everybody walks out of the session with a 50%. The other 10 marks come from the quiz. So you pass in the quiz, I grade it, whatever your grade on the quiz is gets added to that score. So that's how the grading works. I kind of like that setup, and I intend to keep that grading scheme going forward for the rest of the semester. I think that first hour is valuable, so that's always going to be worth 50%. The other thing about the problem sessions is it is good test preparation. So it's a good way to get ready to know what's coming for the test, so that's good to do. I think that's everything. Any questions? No? Okay, good. So last day we talked about electric charge, we talked about Coulomb's law, electric force. We did do it a vector addition. We're going to keep going with some examples today and hopefully get on to talk about electric field as well. So this is a classic problem, 50-50 shot. This shows up on a midterm or final exam. This is a typical one that gets asked. So we have two charges on the x-axis, so on a horizontal line. Q1 is plus Q. It's at the origin. Why don't we put in x equals 0 right here. And Q2 is negative. It's at x equals 5 millimeters. Where can we place a third charge, Q3, so that Q3 will not experience any net force? So the total force on it, when we add it up, is equal to 0. So that's our question. If we wanted to write this as an equation, we would say that the force, so not to experience a net electric force, we would say that the force by 1 on 3 plus the force by 2 on 3 is equal to 0. When we write that as an equation, the net force is 0. This tells us that those two forces must be equal and opposite. Okay, so now we have a goal. We want to place our charge Q3 somewhere where the two forces that act on it are going to have the same magnitude, same size, but opposite directions. So if we look at our picture, we sort of have three choices because infinity doesn't count. It can be out here, it can be in between here, or it could be out here. So we've got three choices. Anybody want to toss in where they think it's going to be?
Somewhere in between.
Somewhere in between. Okay, so we've had that idea. Why don't we have a look at it? So let's see if it's going to be somewhere in between. And thank you, I was hoping the answer was going to be in between. So let's place our Q3. First off the bat, it doesn't tell us what Q3 is. Okay, that's kind of interesting. It doesn't say if Q3 is positive or negative. Let's assume it's positive. And then as we work through our answer, let's take stock of that assumption and see if that was valid. So I'm going to put a little note here, assume positive. So I'm going to put my Q3 right here. That's a little positive test charge, Q3. So what's the direction of the force on this charge due to Q1, left or right?
Right.
It's going to be to the right because it's repelled. So there's the force because of 1 on 3. So Q1, Q2 here. What's the direction of the force on 3 because of 2?
Right.
So that's attractive, also to the right. Okay, so most people, lots of students, when they do this problem, they'll put the charge in the middle. But if we look at those two forces, they could certainly be equal in magnitude, but they can't be opposite in direction. So let's put an X here, because they're not opposite, even though they could be equal. So for our next guess, let's try out here. Let's see if out here is our position. And this really is the way to figure out where the position is to try all three, right? So let's try all three and then we'll know where it has to be. So if we put our charge right here, there's our Q3 now. What's the direction on this one because of this one? To the right because it's repelled. If we look at this setup, forget about Q2 for a moment. We are very far away from a small charge. Are we going to have a big force or a small force? Small force. So I'm going to draw a small vector right here. F1, 3. Okay, what's the direction of the force on this one because of Q2? Definitely to the left because it's attractive. We're pretty close to a big charge. Will we get a small force or a big force? This one's going to be a big force because we have that small distance and the big charge. So I'm going to draw a big arrow. So over here in this region, we meet the requirement that they're opposite in direction, but they can never be equal in magnitude. So this one is not our winner either. Not equal. That leaves us with out here. So let's draw what's happening out here. We'll put in our little positive test charge. The force on this test charge due to Q1 is repulsive. It will point to the left. We're sort of close to a small charge. If we're close to a small charge, we'll end up with a medium-sized force. So I'll draw a medium right there. This Q3 is going to be attracted to this minus 2Q because they're opposite signs. This time we're far away from a big charge. We'll end up with about a medium force. So out here is our winner. Here's where the forces can be equal and opposite. So whatever we get for our answer, we know that the place has to be to the left of Q1 or a negative x value, whatever. Okay, so we've taken care of where it has to be. Let's deal with the opposite part next, or the equal part next. So the forces have to have equal magnitude. So the magnitude of the force of 1 on 3 is equal to the magnitude of the force of 2 on 3. So we write down the statement that they have equal magnitudes. So force of 1 on 3 is K times the magnitude of Q1 times the magnitude of Q3 divided by the distance between 1 and 3 squared. Okay. I've written down a new symbol. I'm going to put that in my diagram. R1 and 3 is the distance between charge 1 and charge 3. R1, 3, I could call that X if I wanted to. There's R1, 3. Fill in my magnitude of F2, 3. That's K times Q2 times Q3 divided by R23 squared. Now that I've written down R23, I'm going to put that in my picture. That's the distance between charges 2 and 3. R2, 3. Okay, the diagram's a little bit full, but hopefully you can see it. So R23 is the distance between these two charges, between 3 and 2. All right, let's look at that equation we wrote down. I've got K on both sides, so I can divide through by K. I've got the magnitude of Q3 on both sides. That tells me two things. It tells me that the size of Q3 doesn't matter, because I can divide both sides by the magnitude of Q3. It also doesn't matter what the sign is. So no matter if Q3 is positive or negative, I'd still be dividing through by the magnitude of Q3. So our assumption is fair. It didn't matter if it was positive or negative. We'd get the same answer even if we chose negative. Okay, so we divide those. Now what we want to do is solve and get our answer. Just to simplify how we write things down, I'm going to call R13 equal to X. So I'll say R13 equals X, that's just for notation. Then I'll see that R23 is going to be R13 plus the distance between the two charges, which is 5 millimeters, or X plus 5 millimeters. So that's just a little bit of geometry. This distance is X, this distance is X plus 5. So good? Magnitudes of my charges. The magnitude of Q1, I've labeled that plus Q in my diagram. The magnitude of 2Q is going to be positive of 2 times Q. So now there are all the bits I have to put into my equation. So I've got Q divided by X squared equals 2Q divided by X plus 5 millimeters squared. It's okay to leave 5 as millimeters. That's not a problem. Just recognize when you get your answer, it is going to be in millimeters. Did you have a question?
Yeah, sorry. The value of 2Q, okay, no, sorry. So it's absolute value, so we dropped the negative.
Yeah. So when we do force calculations, we're writing down the magnitude of the force. We use the magnitude of the charge. You're always putting in the positive values, whether it's positive or negative. Okay, we have a little bit more cancellation now. Q can cancel. Divide both sides by Q. At this point, you have two strategies with your algebra. If you cross multiply your X plus 5 squared up here and your X squared up here, you'll get yourself a quadratic, and you know how to solve the quadratic. Absolutely valid. That's going to give you the right answer. That's going to work. I see a shortcut, which is to take the square root of both sides. Then I don't have to solve a quadratic, and I pretty much don't solve quadratics because I don't have to. So I'm going to take the square root of both sides. So that gives me 1 over X on this side, root 2 over X plus 5 on this side. Now I'll do my cross multiplying. X plus 5 millimeters equals root 2 times X. So root 2 minus 1 times X equals 5 millimeters. X equals 5 millimeters divided by root 2 minus 1. Put that in the calculator and we should get 12.1 millimeters. And then the answer to our question is place Q3 at 12.1 millimeters left of Q1. And we say Q3 here, but really we mean any charge. So any charge we place at that point would have no net electric force on it. Okay, any questions? Okay, looks good.
Where's the 1 come from in the square root?
Oh, down here?
This one.
Oh, I just skipped a line here in the algebra. I took this x to this side, so it was root 2x minus x, or root 2 minus 1 outside x, yeah. Yeah, please, once in a while I will kind of jump a line in the algebra. If it ever kind of like, wait a minute, where did that come from? Please do ask. Sometimes it's hard for me to remember that just because I say a step out loud doesn't mean you can kind of catch it while you're trying to make notes and think about everything as you're going. Yep.
Could you explain one more time why it was okay that we assume positive?
When we got to this step, we had the magnitude of Q3 in for the magnitude of our forces. Since we looked at the magnitude of the charge, it didn't matter what the sign
Oh,
was.
okay, thank you.
The difference in working through the problem overall is if this were a negative, then those two forces would be flipped, right? It would be attracted to that one and repelled by that one, but we'd still get the same behavior. Yeah, good question. Okay, so carrying on. Gonna do another vector addition of forces. This one's pretty common problem. Sometimes we got 4 charges on a square, we put a charge in the middle. Sometimes we put it in the middle over here on one of the sides. You know, that's about all we can really shake it up here. So we have 4 charges. Each one has a magnitude of 1 microcoulomb, and we show the signs in the pictures. Find the net force if we put an electron in the center of the square, and the square has a side length of 1 centimeter. So right off the bat, I'm just gonna label my charges 1, 2, 3, and 4, because it's gonna help me when I do my force vectors. Q1 and Q2 will be my positive charges. Q3 and Q4 will be my negative charges. In the middle, I've got an electron, that's negative. Oh, you can't really see that, can you? Okay. So this little blue one in the middle, that's negative because that's an electron. That's something you're supposed to remember, electrons are negative. If we want to find a net force on this one, first of all, we think about our strategy. This electron is in the vicinity of 4 charges. It's going to feel 4 forces. Those forces are vectors. To find the net force, we'll have to do the vector sum of those forces. Along the way, we might be able to do a little bit of symmetry to help us out because we're at the center of the square. It makes sense that some things are going to be equal and are going to cancel. So there's our idea. To get started on finding my net force, the first thing I'm going to do is I'm going to draw the 4 forces on the electron. I'm going to skip to the next page to draw it because this diagram is a little bit small and I want the picture to be nice and big and clear. So there's a picture where I've put all that stuff in. Here's my electron at the center, still negative over here. I'll make it even bigger. So now to draw my 4 forces. My electron is attracted to charge Q1. So I draw an arrow starting on my electron going towards Q1. There's my force. I'm going to call it force 1. If you prefer, you can write down force of 1 on E for the electron, or F1 is fine. Okay, my next force. The electron feels a force due to Q2. Q2 is positive. Now let's look at some of the symmetry. So at the center of the square, so the distance between the electron and Q1 is the same as the distance between the electron and Q2. So we've got the same distance. Q1 and Q2 have the same magnitude, so the size of the charge is the same. So the size of the force is going to be the same. When I draw my arrow for F2, I'm going to draw it the same length. So it points towards Q2, and it's the same length that F1 was. All right, my next 2 forces, I've got my electron and Q3 down here. Q3 is a negative charge, so the electron will be repelled by this. We're the same distance, same magnitude of force, same distance, same magnitude of charge, we'll get the same magnitude of force. Likewise for Q4, it's a negative, it repels the electron, same distance, same magnitude of charge, same magnitude of force. By rights, those arrows should be right on top of each other, but if I drew them right on top of each other, you wouldn't be able to see them, so I just separated them a little bit, just to make it visually a little easier to see. Okay, everybody okay with the picture? Okay, at this point, you might see some symmetry jumping out. So if you started to think, won't the x components cancel? You would be absolutely correct. And then all 4 of them have a y component that points up, so we think the net vector is probably going to point straight up. If you don't see that symmetry at the beginning, no problem. The math is going to shake it out, so it's fine if you don't catch it. Right, I'm going to go back to my last page now and start putting some notes on that page. So in my process, your first step is to draw all of the forces. Your next step is to figure out the magnitudes of the forces. Okay, so we do magnitude next. The magnitude of my force F1 is K times the magnitude of charge 1 times the magnitude of the charge on an electron divided by the distance between them squared. So let's see what we have to put in this equation. K is Coulomb's constant, 8.99 times 10 to the 9. Coulomb's meters squared, Newtons times meters squared divided by Coulomb squared. Q1, the magnitude of Q1 is equal to 1 microcoulomb, so 1 times 10 to the minus 6 coulombs. The magnitude of QE, the size of the charge on an electron, is 1.6 times 10 to the minus 19 coulombs. Electrons are negative, but in our equation we use the magnitude of the charge, so that's why I wrote down the positive for the magnitude. Now for our R, we're going to have to do a little bit of geometry here to figure out our R value. R on the picture is from charge Q1 to the electron, so this is R. The length of one side is 1 centimeter. So one whole side is 1 centimeter. R is from one side to the center. So this is D over 2, or 0.5 centimeters. And then the length down this way is also D, so from the middle to the top is also D over 2, 0.5 centimeters. Okay, so at the center of the square, so it's half a centimeter from the center, both vertically and horizontally. So my R value is going to be D over 2 squared plus D over 2 squared, or 0.5 centimeters squared plus 0.5 centimeters squared. What we end up with is 7.07 times 10 to the minus 3 meters. Okay. So there's the R value. We've got all the ingredients to put in our equation. Fill in those numbers. Okay, so we write in all of our numbers, and we find for the magnitude of our force, F1, it's equal to 2.88 times 10 to the minus 11 newtons. Okay, so our calculation tells us that's the size of the force on the electron due to charge 1. Here, we can go back to our picture. We can remember all the things that we said, that those charges were at the same distance and they had the same magnitudes, and we drew those forces the same length. Here we can apply that symmetry. So we can say due to symmetry, the magnitude of F1 is equal to the magnitude of F2, is equal to the magnitude of F3, is equal to the magnitude of F4, and they're all equal to that 2.88 times 10 to the minus 11 newtons. If you were doing this problem and you didn't catch the symmetry, you would do this equation 4 times and you'd get the same answer each of the 4 times. Not a problem, that's totally valid. Use of symmetry generally just makes it a bit quicker for you to get through it. Okay, so now we've done step 2 in our process, which is to find the magnitudes of the forces. Step 3 of the process is find the components of the forces. So I'm going to write those notes on the next slide. So I'll do the x components and the y components separately. If you were on a test and you said due to the symmetry of the problem, the net x component is 0, I would mark that correct, that's fine, it's absolutely true. I'm still gonna go through the process of finding the components, because if you don't see the symmetry and you actually calculate it, then you would just figure it out from the calculation. So if we're finding components, we need an angle. This angle is 45 degrees because we're cutting through on the diagonal of a square. Everybody okay with that geometry? If you didn't like just recognizing that it was 45, then you could see that tan of this angle is d over 2 divided by d over 2. Solve for theta, that would give you 45 degrees. So when you have the same opposite, same adjacent, you get 45 degrees. Okay, for my f1, the x component points to the left. So f1x is going to be negative times the magnitude of f1. f1x is adjacent to 45, so minus f1 cos 45 degrees. You could draw it in if you wanted to. This is going to get real messy, f1x. f2x points to the right, same angle, 45 degrees. f2x is positive because it points right, plus f2 times cosine 45. Okay, when I said it out loud, I said f2x was f2 times cosine 45. Then I made a substitution, but I said f2 was equal to f1. So that's why I wrote f1 here, because all 4 of those forces have the same magnitude. f3x, that points to the right. Here's my f3x. It's got a magnitude of f3 or f1 times cosine 45. My f4x points to the left. So f4x is negative f4 or f1 times cos 45. So I filled in here in this step that f1, 2, 3, and 4 all have the same magnitude as f1. When I do my sum of my x components here, I see that they all add up to be 0. Okay, so there's my x components. So these two cancel, and it adds up to be 0. Go to the y components next. For my y components, I'll have to use sign. So f1y points up. f1y is up here. Because it points up, it's positive. Because it's opposite the angle, we use sine. So I've got f1 times sine theta, or sine 45. My f2y also points up. So f2y is equal to positive f2 or f1 times sine 45. f3y also points up. So that's plus f3 or f1 times sine 45. And then f4y also points up. f4y is equal to plus f4 or f1 times sine 45. So there are your 4 y components. They've all got the same magnitude and they're all times sine 45. So my net y component is all those 4 added up. So I've got 4 times f1 times sine 45. All good? There's a lot of very fast components. I guess you're pretty comfortable with that from 1020 or 1050. So we can do that in the calculator. That's equal to 4 times 2.88 times 10 to the minus 11 newtons times sine of 45 degrees. That works out to be 8.14 times 10 to the minus 11 newtons. Then to finish, we write our answer as a vector. The net force on that electron is 8.14 times 10 to the minus 11 newtons. It's all y components. So it's all in the y direction, or j hat. And this answer matches what we thought we would get when we looked at those vectors. The x's have equal amount left and right, so the x's summed up to be 0. All of the y's point up, so the total vector is in the y direction, and it's bigger than it was individually. Questions? Good. Yeah.
So if we were to ever get a diagram like this on a test or an assignment,
Yeah.
would we have to then do an arrow pointing to the net force direction?
Oh, to draw your net force in the end?
Yes.
Yeah, you don't have to. You can if you want to, though.
Okay.
So there's our net force for our last step. Okay, so we'll take a break with those vector calculations. We will come back to them in a little bit. And we will move on to electric field. So to get to the idea of electric field, because it's kind of interesting and kind of weird, let's just go back to physics 1020 or 1050 for a moment. And when we talked about forces in 1020 or 1050, or at least I did anytime I taught the forces, you always think about the agent of the force. What makes the force? Because that's a really good question, what makes a force? So for example, a friction force is caused by an interaction of rubbing between two forces. A tension force is caused by the pulling of a rope. So the agent of the forces is always really important. When you get to talking about gravity, the loose way to talk about the agent of that force is to say the earth. Things fall down because the earth pulls on it. Well, that's sort of funny because the earth doesn't pull out its hand and pull down on it. So how does it pull? What does that even mean? We know a gravitational force is a long-range force. It doesn't have to touch. So if a mass m feels a gravitational force, the way you would write down that force is just to write m times g. In 1020 or 1050, you didn't put an arrow on top of g, but it does by rights belong there. Force is a vector. Mass is a scalar, so the other thing that's a vector has to be g. That's where the vector nature of that force comes from. In high school, or 1020 or 1050, you would call g the acceleration due to gravity. That's a reasonable description, but it's kind of more than that. It turns out that if mass m feels this gravitational force, this g is the agent of that gravitational force. So mass feels the force because it exists in g, where g is called the gravitational field. So a gravitational field is a real thing. You can calculate it by doing the force of gravity divided by the mass. You can calculate gravitational fields around big massive bodies. If you plotted the gravitational field around the Earth and the Moon, it would look like this. Now we're getting into talking about the curvature of space and general relativity. All of that stuff is very interesting. It's in your textbook. If you wanted to have a read about it, I would recommend Stephen Hawking's Brief History of Time. It's an outstanding book with a really good explanation. This is all you're going to get from me, is that you can plot gravitational fields around planets, and it looks sort of weird like this. In close to the Earth, the gravitational field points straight inwards, and that's why things fall down, because they're pulled by that gravitational field. So G, this gravitational field, is made by the Earth, this big massive body, and small masses m, when they get in this field, they feel these forces. Okay, so that's another take on gravity, force due to gravity. Let's take that idea and apply it to electric fields. We know that charged objects will feel electric forces. You can see it when you try and bring two balloons together. We know it's true because of atoms and molecules and molecular structure. We know that that force is a long-range force. It doesn't have to touch, so it has the same kind of behavior. So we know that a charge Q feels an electric force that electric force we called F. Because it feels an electric force and it depends on the charge, our expression for electric force could be written as charge times field, where the field now is the electric field. So this E is our electric field, and I'm going to say specifically electric field vector. So G is a gravitational field that tells masses how to move. E is an electric field vector that tells charges how to move. So that's what an electric field is. What else can we say? So if we wanted to figure out our electric field E would be the electric force divided by the unit charge, just like our gravitational field is force per unit mass. So this electric field, the gravitational field was made by the big Earth, and it was felt by a little mass. This electric field is made by a big charge, and it's felt by a little charge. So we'll kind of keep going with those ideas, that sort of analogy. Okay, are we good there with the concept of an electric field? Okay. So let's get to work on figuring out electric fields. If we wanted to tell if there was an electric field at some point in space, the way we would test for an electric field is we would take what we call a test charge. And the test charge would have a symbol of a lowercase q. Sometimes it's called a probe charge. I think your book really likes probe charge, but more often people will say test charge. This test charge is always small and it's positive. Okay, just like an apple is small compared to the Earth, a test charge is small compared to whatever makes the electric field. So we're going to put our test charge at some point in space. So let's say it's right here. Then we ask, does our charge feel an electric force? Does it move because we place it in this place in space? Well, if it does experience an electric force, so let's say yes, it feels a force. The electric force we can draw. That would be the electric force. If we have a charge and it feels an electric force, it must be in an electric field because the field is what makes the force. So our conclusion is there must be an electric field. So our electric field E would be the force divided by the charge. If this charge is positive, then the electric field is the force divided by some number. That electric field would be in exactly the same direction. Different size, different units, but same direction. Some things that are good to know about electric field. The units of electric field are newtons per coulomb. We're going to use that for a long time. There is another acceptable unit, which is volts per meter. So I'll put that in there now for completeness, but we'll come back around to that when we get to potential and potential energy. The magnitude of the electric field is called the electric field strength. And our electric field is made by a source charge. And that's just like saying the Earth makes a gravitational field, so some great big old charge makes an electric field. Our next point you might not think about, but it's still definitely true. So if I hold my pen up in the air and I let it go, it's going to fall down, right? No brainer. If I put my pen away, gravity doesn't turn off. Gravity still exists. Likewise with electric field, even if there's no test charge, we still have an electric field. So that's there whether we choose to put a charge in or not. So electric field doesn't disappear because we put our charges away. So exists even if Q is removed. And last, so if this electric field exists, even if I take away this charge, then that field doesn't depend on this charge. If I can take it away with no effect, then there's no dependence. Okay, still good? So now here's just a bunch of stuff I've written down. It's a summary of all the different things we've already said. So the electric force on a charge is exerted by the electric field. It's another way of saying the electric field is the agent of the electric force. The electric field is created by source charges. Our test charge has a symbol of small q. We often give our source charges a symbol of capital Q to kind of indicate that they're bigger than the test charges. Electric forces and fields are both vectors. And the two vectors we wrote down is that electric force is charge times electric field. And electric field was the electric force divided by the test charge Q. Just like there's gravity everywhere in space, there is also electric field everywhere in space because the universe is full of charges. This one, we'll kind of get to this a little bit more. You'll see this as we go through problems. But a charge doesn't feel its own field. So just like there's no force of gravity on the Earth due to the Earth, there's no there's no electric force on a big charge due to the charge itself. So it doesn't feel its own field. Okay, next let's talk a little bit about this equation and directions. Make sure we're okay with that part. So if we have an electric field, here's our electric field E, and we place a positive test charge, plus Q. So this is our test charge Q. This electric field here, this is made by some other source charges that are somewhere else. So this exists because of those source charges. When I place a little test charge here, let's ask about the force and the direction of the force. So my electric field has some magnitude and it points to the right, so I can say that it's E times I hat. My electric force is that charge Q times that electric field, or Q times the magnitude times I hat. That electric force is also to the right. So there's my electric force. Good? That doesn't feel groundbreaking. All right, what if I didn't put in a positive test charge? What if I put in a negative test charge? Then what would the electric force on that charge be? So for this one, my electric force hasn't changed, my electric field hasn't changed. It's the same magnitude to the right. This time my little test charge is negative Q. So my force on that little test charge is the charge minus Q times the electric field vector, minus Q times E times I hat. I've got a minus times I hat here. This points to the left. So this time the electric force is in the opposite direction. So this leads us to a conclusion. If our little test charges are positive, then force and field are parallel. If our test charges are negative, then force and field are anti-parallel. Or opposite direction, however you'd rather put that.
What does that arrow represent that you put after the E's?
The arrow that up here,
Yeah.
that's E with an I hat, tells you that it's pointing to the right. Yeah,
Okay.
so I hat means to the right. Okay, so let's do a quick example of this F equals QE, and let's do it based on the example we did a minute ago. So our example from a few minutes ago, we had our 4 charges on the square. We placed the electron at the center of the square, and we found the net force on that electron. So that was something we did a minute ago. Let's go back to that example. Got our 4 charges, each with the same magnitude. The square has a length of 1 centimeter. We found the force on an electron at the center of the square. Let's find the electric field at the center of the square. So here was our electron at the center. Found that it had an electric force that pointed straight up, and there's our electric force. We want to find the electric field. You know that electric field is electric force divided by the charge. So this here, this electric force, this is the force felt by the electron. This Q is the charge that's feeling the force. So this one is the electron. This is the electric field made by the source charge or charges. Here we have 4 source charges, 1, 2, 3, and 4. So those outside charges are the ones making the field. Okay, so that's what all those symbols stand for. So we'll put in our values. So our electric force is 8.14 times 10 to the minus 11 newtons, J hat. The charge on the electron is minus 1.60 times 10 to the minus 19 coulombs. Gives us an electric field of negative 5.09 times 10 to the 8 newtons per coulomb, J hat. Okay, some things to put in here that are kind of important. So our electric field is negative with a J hat, so electric field points down. Because we said if we place a positive and a negative test charge in the same field, they have forces in different directions, tells us that the sign of the test charge matters. So in this equation, we include the sign. So I never ever put in the magnitude of that charge. It is the charge itself. Sometimes it's positive, sometimes it's negative. So that has an impact on the direction of the vectors. Magnitudes of electric fields, they're often going to be up there around 10 to the 8, 10 to the 6, 10 to the 10 ballpark. So electric fields are big, so don't be surprised if those numbers turn out big. Okay, questions there? We only have 3 minutes. I don't think I have just time to really work out how to calculate the electric field. Is everybody agreeable to quitting 3 minutes early? Nobody ever says no to quitting early, right? Yeah, okay, so we'll jump into this on Friday.